Okay, so besides after the class is over, I gotta head down to New Orleans. So we all want to get out of here. No, I'm not. That doesn't mean I'm gonna end class now.
Always travel.
Yes, that's professional life. Well, especially those who are able to get a grant to support their travel, which I did.
That's fun.
Yes.
Is this another conference? Or?
Oh, actually, this is a personal thing, unfortunately.
Oh.
Unfortunately, that's a good thing, huh?
Under circumstances, no.
Oh,
I'm
no.
sorry.
I'm so sorry to hear that.
Family member health problems.
Oh, goodness.
So yeah, good to see people, but yeah.
Yeah.
One of those things. Yeah. Okay. Well, gets me out of Friday faculty meetings. Okay. Started on solving ordered differential equations, or really initial value problems. So a very quick recap of where we're at. We saw one method for solving this differential equation and initial condition. And that method is, what do we call this method? Or how do we say it?
Euler's.
Very good. Euler's method, and that is each new solution value, so this is approximation of the exact solution at time tn plus 1 is equal to the previous one plus h, which is the time step. So it's just the difference between two consecutive time values. So you plug your current time and current solution value into your time derivative f, multiplied by h, add on the previous solution value, and you get the new solution value. So this is the whole method right here, starting from n equals 0, 1, 2, and so forth. So in other words, your initial value is what goes in there first, as well as your initial time. So your initial condition kicks things off, allows you to go from y0 to y1, then y1 and t1 get plugged in here to give you y2, and you just keep going until you reach your final time, whatever that might be. Okay, and after an excruciating series of manipulations, what we saw was that the error difference between the exact value and the approximate solution value at the same time is, I'm not going to write out the whole formula, we don't really need that, but it's big O of h. In other words, it's proportional to h, the time step size. So we saw that as h goes to 0, the approximate solution does converge to the exact solution. But because it's proportional to h to the first power, we say that this method is first order accurate. Okay. And we want to do better. That's what today is about. So I'll show one approach to getting higher order accurate methods. The way I derived Euler's method last time was to use Taylor expansion, but I only took it out to really use up to the first derivative term. And so if we only use first derivative, then all we can hope for is first order accuracy. If we take a Taylor expansion out of y a little further, then that gives us a way to achieve higher order accuracy. So what I'm going to do is give you an example of how such methods are obtained. Okay. So this is a family of methods called, so to get higher order accuracy. In other words, if the error is order h to the p, where p is greater than 1, you can use what are called Runge-Cont'd methods. Okay. One of those names, Runge, actually came up last semester in 460. There are a handful of you who were in that class. Does anyone remember where that name came up? By any chance? I know it was several months ago. Runge's example from polynomial interpolation. Yes. Yeah, but you interpolate equally spaced points, high degree, it goes badly. So Runge was pretty diversified. And the contributing business is completely separate. So we use higher order or higher degree Taylor expansions. All right. So as an example, what I'm going to do is I'm going to specify a form for this higher order accurate method where certain parameters are unknown, and we'll try to figure out what those parameters should be using Taylor expansions. So if I time-stepping method of this form, so you see it'll start out looking like Euler's method. Yn plus 1 is equal to yn plus some other terms. And so I'll have h. But what I have now is going to be different. So I'm going to have af of tn yn, where a is unknown, plus bf of tn plus alpha, yn plus beta. Okay, so I have 4 unknown parameters, a, b, alpha, and beta. So I want to figure out what those parameters should be in such a way as to at least get second order accuracy. That's really all we're going to be able to get in this case. All right. Now, so what I can do is show you how I would find these parameters. And we're going to get them by matching 2 Taylor expansions. The first Taylor expansion will be of y, the exact solution, at time tn plus 1. I can Taylor expand that around tn. So then I would have h y prime of tn plus 1/2 h squared, y double prime tn, and so forth. I'm not going to need to go any further than that. So this is one Taylor expansion. And then the other Taylor expansion is going to come from here, where I just Taylor expand f. So f is a function of 2 variables. So I'm going to need to perform a multivariable Taylor expansion. And I know that Taylor expansion of 1 variable is enough of a horror show as it is. So why not make it? So what I have here is, for the method, y of t. So I'm going to write this y of tn plus 1 equals y of tn plus h A. So here I'm going to write this as f of Tn y of Tn. So I'm substituting the exact solution in for the numerical solution. Plus B f of, okay, this is where things are going to get messy. I need to write it on another line. Okay, so what I'm going to do is I'm going to expand this around Tn and y of Tn. So the first term will be just that, f of Tn, y of Tn. And then what happens is, normally your next term, your second term in a Taylor expansion, involves the first derivative. Well, this is a function of two variables. We're going to have two first derivatives, two first partial derivatives. So I would have partial of f with respect to t at Tn y of Tn times the change in t, n, which is alpha, plus partial of f with respect to y at Tn y of Tn. Oh, I'm going off screen here. Okay. Times the change in your y variable. That change is beta. So I'll fill that in here. And there would be other terms, but I'm not going to need those. We'll just cut it off at this point. And then there's also going to be, I had to say plus error, because what I'm doing is I'm substituting the exact solution into the numerical method. When you do that, because the numerical method is not a differential equation, it's only an approximation of it, there's going to be some error. And the idea is we want to make the error at least order order h squared. Oh, actually, I need to include a factor of h in here. So I want this to be order h squared, meaning this entire term should be at least order h cubed. So if I've done that, then I'll successfully obtained a second order accurate method. And I realize having this factor of h in here is kind of weird. Like, why did I throw that in there? It's because if I were to write this equation, rearrange it algebraically to make it look like the differential equation, I'd have y of Tn plus 1 minus y of Tn over h, and that is approximating y prime. But I have to divide by h to get there. So that's why I need to have this factor of h sitting there. So we want order of h squared error when we're actually looking at the true differential equation versus the approximate in the same form. That way, the overall error will be the same power of h squared. When we get to convergence analysis, which is next week, that'll become more clear. So for now, just go with me on this. All right. Or I can always say, it's in the book. Okay. So what I want to do is I want to have as many terms as possible match between here and here. And choose A, B, alpha, and beta to make terms match. So if I can get all the terms up to order h squared to match, like up to this point, like get rid of this one, I have this cancel of something down here, then what's left over will be order h cubed, so that'll be accurate enough. Okay, now, if you look at what I'm matching, certain things already match. So we don't have to think about those anymore. So that, all these things already match. Also, this factor of h matches with what's down here. So I'll cross out one factor of h also. So that cuts down the size of what we need to match. Okay, so what's left that I haven't crossed off yet. So I have y prime Tn plus h over 2 y double prime Tn. And then down below, what I have is a f plus b plus partial f with respect to t times alpha plus partial f with respect to y times beta. Okay. Now, at first it seems like what I have above and below look nothing alike. But that's easily fixed. Because y prime equals f of ty. So this is f of Tn y of Tn. So you see how we have that down here also. So that's going to be a lot easier to match. And then y double prime of Tn, I can write as derivative with respect to t of y prime of Tn. But here I make the same substitution. Y prime is equal to f. Now, if I carry out the derivative of this with respect to t, this is a function of two variables. So by chain rule, it'll be partial of f with respect to t at Tn y Tn. Plus, by chain rule, partial of f with respect to y times the derivative of y with respect to t. But what's dy dt? Or y prime? As I just used 2 minutes ago. F. So I can fill that in too. Okay. So y double prime is now all this, which, as you can see, bears quite a resemblance to what's above. So now if I take all this, put it in there, and then match it against what's down below, I'll have. So I have, from this part, I have f of Tn y of Tn plus h over 2 partial f partial t, which I'm going to leave this out. I'm tired of writing it. Plus partial f partial y times f. So actually, I'll just write this also as f. So at least I'm abbreviating consistently. Okay, so this is, all of this is times h over 2 because of that up here. So that's what I have from the first expression. Second expression, I have a times f plus b times f plus partial of f with respect to t alpha plus partial of f with respect to y beta. Okay. So, the expression AF is unfortunate, but it happens. So now if I compare these two, picking up terms involving partial f with respect to t or partial with respect to y, or just plain f by itself, then I have f over here must be equal to AF plus BF. So it means that A plus B is equal to 1. So that's one condition that we have. And then I have, if I look at partial of f with respect to t, look at the coefficients, match them up. I have h over 2 must be equal to b times alpha. And then if I look at the terms partial of f with respect to y and make them match, I have h over 2f must be equal to b times beta. So those are the three conditions that need to be satisfied in order to make this method have second order. Because then the next term that will show up from here will be order h squared term from this, and order of h cubed term overall. So we want to deal with it because all we want is second order accuracy. Okay, so any questions about how these conditions for A, B, alpha, and beta were obtained? So you're matching a single variable Taylor expansion of the exact solution versus a double variable Taylor expansion of every instance of calling f. And you're expanding around the same time. First, single variable Taylor expansion of y, you're expanding around Tn. For f, you're expanding y of Tn. Okay, now we have 4 variables, but we only have 3 conditions. That means this does not have a unique solution. That's okay. We're actually going to get 2 methods out of this that are both second order accurate. Now, the first choice, because we have a plus b is equal to 1. So we're free to choose a and b however we like to satisfy that. And then once we do that, then that will uniquely determine everything else. So the first choice, set a equals 0. Because then that way one invocation of f is gone. So that means that b has to be 1. And then alpha would have to be h over 2. And then for beta would have to be h over 2 times f of EMY. So now when we go back to the original form of a method that I had in mind, this is what we get. Yn plus 1 is equal to Yn plus hf of Tn plus h over 2, that's alpha, and then Yn plus h over 2 f of Tn Yn. So this is a second order accurate method. It is called the midpoint method. Now, those of you who took 460 last semester, or any semester, I recall from numerical integration, one of the rules we saw was the midpoint rule, where you evaluate your integrand at the midpoint of your interval. This is the midpoint of the interval in time. You're going from Tn to Tn plus h. So you strike at the middle there. And then this is actually the Euler's method approximation of y at that midpoint. So you can think of that as like we're evaluating f at t of n plus a half, and then y n plus a half. We're just approximating it this way. Okay, but yeah, it's reminiscent of the midpoint rule for numerical integration. Okay. So the error is order h squared. So in other words, with Euler's method, you reduce h by a factor of 10, error is reduced by a factor of 10. But with the midpoint method, it's reduced by a factor of 100. All right. Choice number 2, a plus b must equal 1. So I'll set a and b both equal to 1/2. But if we go back to those conditions over there, if b is equal to 1/2, that means what should alpha be equal to? Because look over there. Yeah, just h, because the 1/2 has already been taken care of. What should beta be if b is 1/2? HF. All right. So the method that results is this one: yn plus 1 is equal to yn plus h over 2 times f of tn yn plus f of tn plus h yn plus hf. Okay. So this is the Euler's method. Actually, it's just flat out Euler's method that approximates y n plus 1. Now, this method is called the explicit trapezoidal method. It's called that because it's reminiscent of trapezoidal rule for numerical integration. So it's also second order accurate. So I'm just going to write over here what the corresponding integration rules are that inspire the names. So you can approximate an integral by b minus a f at the midpoint. So this is the midpoint rule. Hopefully this rings a bell for those of you who took 460. And then the trapezoidal rule is integral of f is approximately b minus a over 2 f of a plus f of b. Okay. Oh, actually, didn't need to go that far. All right. Okay. So here we're approximating the integral by evaluating f at its midpoint between a and b. Here we're evaluating f at both endpoints a and b. Same thing here. Midpoint in time, either endpoint in time. And then solution values that correspond to that. Okay. So these are the simplest examples of Runge-Kutta methods. The first one, the midpoint method, is called a one-stage method, whereas the second method, the trapezoidal, is called a two-stage method. Now, a stage of a Runge-Kutta method that is defined to be an evaluation. Most of you haven't done the quiz yet. It's an evaluation of f. So midpoint method only needs to evaluate. Oh, wait a minute. I totally blew that. They're both two-stage methods. It's how many times you have to evaluate f to implement a method. So even though we only have one call to f out here, but we also have to evaluate f at this point, tn, yn, and then this other point here involving the midpoint. So two evaluations of f are required for both. So neither method really has an efficiency advantage over the other. It's just that, so you've been sure if you get second order accuracy for both. This one, it looks like you have to evaluate f 3 times, here, here, and here, like the way I wrote it, except 2 of these evaluations are at the same point. So if you implement it more carefully, then you see there's only 2. So in fact, that leads to, this is not really the way that Runge-Kutta methods are normally written. So I'm going to put it in that form, show you a more important Runge-Kutta method from there. So it's common when writing Runge-Kutta methods, this is how you would put them in code, to write out however many stages you need. So you need, whatever evaluations of f you need, you just write those down up front. So you're basically getting your ducks in a row, and then you combine them in the right way to get yn plus 1, which is always the end goal. So this way it's more apparent that you have, including to me apparently, that you have 2 stages in both methods. Okay. So the midpoint method versus the trapezoidal, or I should say explicit trapezoidal. Soon before we finish, I'll talk about explicit versus implicit methods. Now, so the way we write the midpoint method stage in terms of stages, first stage we'll call K1, which is HF of Tn, Yn, and then the same thing over here. So that's almost always the first stage. Okay. Then the second stage for midpoint method is HF of Tn plus h over 2, and then Yn plus 1/2 times K1. So what I have here for K1, that's what goes down here. So we have to compute these in order. And then, finally, Yn plus 1 is equal to Yn plus, and we just have K2. So that wraps up your method. Okay. Now, on the other hand, with explicit trapezoidal, our second stage is HF of Tn plus h, and then Yn plus K1. So we're not in that case. But then Yn plus 1 is equal to Yn plus 1/2 K1 plus K2. Okay. So you should convince yourself that what I've written over here is equivalent to what I wrote over there. Same methods. But here's more obvious how many stages are involved. And it's typical for stages to depend on earlier stages, the results of it. All right. So now, in this same form of writing out stages, I'll write out the best known run kind of method. It's commonly known as the fourth order run kind of method. Now, there are actually many run kind of methods that are fourth order, but this is the best known, so this has this name. Oh, I should mention the my editor for the textbook suggested that, given the long name, fourth order Rangakutta, and how often I use it in the book, that I refer to it by an acronym. But what would the acronym be? Yeah. He seriously wanted me to call this fork method.
How long has he been an editor?
A matter of weeks, actually. So, at least at this publisher. So the newness is showing. I briefly contemplated it, then I realized that my colleagues in this community would never let me live it down. So I appreciate his efforts, but yeah. Oh, it's a fourth book, yeah. I mean, I guess the book would become known. I guess they always say there's no such thing as bad publicity, but this is my first book, so. So, the fork method. Is the same first stage. We're actually going to have 4 stages to get fourth order accuracy. So K2 is HF of, so we go with Tn plus H over 2, so the midpoint again, Yn plus 1/2 K1. And then, third stage is very similar, same point in time, but then we have 1/2 K2, and then K4 would be HF of Tn plus H, Yn plus, okay. Actually, now that I think about it, this last part seems kind of strange. This is what I get for always doing these formulas from memory. That if you've been doing it from memory for as many years as I have. Come on. I just love USM Internet. Okay. Okay. No, what I have in the book is actually right. So, K3. The reason I thought that was kind of strange is here we have Tn plus 1. So you think this is the approximation of Yn plus 1. But K3 is an approximation of F at the midpoint in time. So you think we just only have to take a half step more. But nope, they say a full step. It's like, okay, I believe them. So just making dang sure. The book's about to go out, probably should print next month. So then we combine these. So K1 plus 2K2 plus 2K3 plus K4. All right, so that's the fourth order run kind of method. So if you reduce H by a factor of 10, the error is reduced by a factor of 10,000. So it's way, way more accurate than any of the other methods described so far. But it takes more work per time step.
Yeah.
But when you get a higher order of accuracy, it's well worth it. So the overall amount of computation from T0 to your final time it's still going to be far less to get this increased accuracy. Now, we'll see if any of you are on your toes here. So notice, the K1 comes from the left endpoint in time. K4 comes from the right endpoint in time. But K2 and K3 come from a midpoint in time. Does anyone remember, this is from, again, a 460 question, integration rule where the midpoint was given 4 times the endpoints? Well, you didn't take it, so but anyone who did, there's a handful of you, or 4 of you, I guess. Well, Simpson's rule. Simpson's rule is that the integral of f is approximately b minus a over 6 times f of a plus 4 f at the midpoint plus f of b. So, whereas the trapezoidal rule would give only twice the weight to the midpoint. Okay. All right, so it's somewhat reminiscent of that. And the thing is, trapezoidal rule, second order accurate. Midpoint rule, second order accurate. Simpson's rule, fourth order accurate. At least the composite versions. Okay. So these would be essential run kind of methods. And there's many more that are a lot more sophisticated than this or have higher order accuracy. But so they're all derived in a similar fashion by taking these lengthy Taylor expansions of y and f and just matching up terms as far as you can, and figuring out what these all various constants should be. So it's a pretty laborious process. Okay. Now, so now I'm going to talk about a different sort of method, because I refer to this as the explicit trapezoidal method. So there's an explicit method. What's an implicit method? Now, some of you had to discuss this in the quiz already, or have been very proactive about that. So congratulations, you've done all your quizzes. So now I'm going to take a little time to talk about what is an implicit method, because these methods are extremely important also. So let's give you a couple examples of implicit methods. First is called backward Euler. That's very similar in appearance to Euler's method that you've seen. The only difference is where we evaluate f. Because Euler's method evaluates f at tn, yn. Now we evaluate at tn plus 1, yn plus 1. The other that I'll mention now is the implicit trapezoidal method. I put it in parentheses because by default, if you refer to a trapezoidal method, it's this one, as opposed to the explicit one that I gave earlier. So, again, similar in appearance to the explicit trapezoidal method. We have f of tn yn plus f of tn plus 1, yn plus 1. Now, like Euler's method, so Euler's method that I showed you earlier is often called forward Euler to distinguish from backward Euler. So this is first order accurate, just like forward Euler is. And the this implicit trapezoidal method here is order h squared. It's second order accurate, just like its explicit cousin. Okay. Now, what makes a method implicit? This. We have yn plus 1, the value you're trying to compute, appearing on both sides of the equation. So when you have that, that means you cannot just plug and chug. Yn plus 1 is unknown. So you know yn, you know tn, you know f, but not this. So for both of these, or implicit methods in general, you must solve for yn plus 1. So in other words, you have much more work to do per time step. And you might think, well, why do it then? Because we already have these explicit methods where we don't need to do this. And the reason why is, with implicit methods, generally you can use a larger value of h. With explicit methods, you often, especially for certain kind of equations called stiff equations that we'll see later, the only way you can get a physically reasonable solution is to choose an extremely small value of h. Whereas with implicit methods, in some cases, you can choose h literally as large as you want and not have to worry about physically unreasonable solutions. And this gets into what's called stability, which I'm not going to talk about now. That's going to be when we get to convergence analysis. The last section we'll cover in this chapter. So there's a trade-off. Explicit methods, only little work per time step, but it got to take a lot more time steps. Implicit methods, each time step is more expensive, but you need to take fewer of them. So you have to judge based on the problem you're solving, which is a better option. So there are certain classes of problems for which people generally use implicit methods, whereas explicit might be favored for other types. It just depends. Okay, now, if you're going to use an implicit method, the question is, now, how do you solve for yn plus 1? Because for basically you have an equation like this or this that's a nonlinear equation. How do we solve nonlinear equations? What methods are at our disposal? That we have been talking about for weeks.
Taylor series.
What?
Taylor series?
No.
No. Okay, just kidding.
What? Newton's method.
Newton.
Also? Others? Secant? Fixed point iteration. Yeah, those kind of methods from the previous chapter you can use. So as an example, let's suppose we use fixed point iteration. Because these two methods are already kind of written in that form. You have a variable you want on the left side, and then it's buried somewhere on the right side. So it's kind of like already in that x equals g of x kind of form. So fixed point iteration, I'll give an example involving backward Euler. The nice thing about using root finding methods for these kind of this kind of situation is, okay, for instance, what are the drawbacks of Newton's method? You just had to do in a test. Okay, and what's the other one?
Has to be reasonably close.
Yeah, you need a good initial guess.
Yeah.
Well, you have a good initial guess built in already.
Yeah.
Your value from previous time step, especially if h is small. Or, in fact, what you could do is you could take yn, go ahead and use an explicit method, like Euler's method, to get an approximation of yn plus 1, and that could be your initial guess. So an initial guess, a good initial guess, is already available. So I could do, for instance, yn plus 1 iterate 0 might be yn or yn plus hf of tn yn. So either one of these would be a decent initial guess. Then your iteration, oh wow, my usual, is yn plus 1 k plus 1 is equal to yn plus hf of tn plus 1 yn plus 1 k. So this right here is your fixed point iteration. So you get your initial guess, then you keep substituting it into the right side to get your new iteration, then you keep plugging that back in, just like fixed point iteration any other time. Now, what's more is we can get an idea, we can actually figure out how to ensure convergence. What do we need to be true of fixed point iteration? Like this right side here is like your G. What needs to be true of G to ensure that fixed point iteration will converge from the test? What? Yeah, G prime, absolute value of G prime must be less than 1. Well, in this case, G prime of x is equal to, well,yn's a constant, so forget that. So you have h times partial of f with respect to y. So, well, you know what f is. You can get an idea of what its partial of f with respect to y is. So, all you're going to do is choose h to be small enough, because you're free to choose it. You choose that to be less, so that the whole expression, f h df dy, is less than 1 in absolute value, and you're guaranteed that your iteration will converge. And then similar for trapezoidal method, in that case, h over 2 partial of f with respect to y must be less than 1. So that actually gives you a little bit more leeway. You can choose h to be twice as large. And also you get second order accuracy in that case. So that's a nice bonus there. These are the kind of methods, so problems that root finding methods are extremely useful for, because some of the things you have to worry about with other functions, you don't really have to in this case, such as having the good initial guess. Okay. I might have accidentally given away an answer to a homework problem, but it wouldn't be the first time. Yep, I did. You're welcome. Okay. With Newton's, it would be more difficult because you need to compute the derivative of f, and that's going to be a big. That would actually be involved in your computation, which is not so good. But because Newton's method converges so rapidly, and you already have error because of your time-stepping method, what people often do is they just go ahead and say, we're just going to perform one iteration of Newton's method. That's it. You already have a good initial guess. And then they move on. So your method's not spinning its wheels. Okay, it's 4:48, but I'm actually done. So good luck in your test. And getting a seat for a test. Okay, so we'll continue with all this stuff next week.